Hey everyone, welcome back. So in our last session, we got our hands dirty with project integration and version control. But today, well, we're zooming back out. This is a Forge College explainer, and we are diving deep into the theoretical blueprints of Ethereum accounts and models. Specifically, we're going to crack the code on internal versus external account interactions. Okay, let's just dive right into this, because understanding the origin of a state change on Ethereum is basically the master key. It's how you figure out why some transactions stick around permanently and why others just seemingly vanish into thin air.
Here's our agenda for today. 1. The commit boundary. 2. External transactions. 3. Inside the internal calls. 4. A real-world DEX swap. 5. The comparison breakdown. And 6. Wrapping up.
Section 1. The commit boundary, or general contractors versus subcontractors.
To make this intuitive, I want you to think of the Ethereum network like this massive buzzing construction zone. The key mental model here is to treat the external transaction as a database commit boundary and internal calls as operations inside that boundary. Think about it. On a real job site, subcontractors can build walls, run wires, install pipes, but none of it is officially part of the house until the city inspector signs off on the general contractor's overarching permit. If that inspection fails, the whole thing gets ripped out like it never even happened. It's the exact same on Ethereum. State changes, like storage updates and balance adjustments, they're totally transient during execution. They only become durable, permanent chain state if the outer transaction officially commits.
Moving to Section 2, meet external transactions, our general contractor.
So looking closely at the general contractor, which represents the external transaction, we see they're the ones really doing the heavy lifting and pulling the permits. They originate from an externally owned account, or EOA, and actually sign the official paperwork. Notice how they consume a nonce? That's kind of like a sequential permit number that ensures absolutely no job is duplicated. Plus, they pay the gas for the entire execution right out of their own pocket. Because they're the ones directly interacting with the public city office, they are completely visible in the mempool and in block listings. Most importantly, though, they form the top-level execution context. Basically, the buck stops with them.
Section 3. Inside the internal calls, our subcontractors.
Okay, the crucial point here is contrasting these two directly. Look at how the internal calls, our subcontractors, operate. They do not originate from outside the network. Instead, they're generated by opcodes like call or delegate call while a transaction is already running. Because of this, they don't get a unique permit number, they do not consume a nonce at all. They're entirely hidden from the mempool, basically sneaking onto the job site only after the general contractor has started working. And this is key, they share the main gas budget. A subcontractor doesn't pay for the building materials out of their own pocket, right? They just use the gas budget that was forwarded to them by the general contractor.
Now, as any good manager knows, you have to tell your subcontractors exactly where to build. I mean, imagine a plumber showing up and installing a beautiful new sink literally inside your neighbor's house. That is the fundamental difference between call and delegate call. A standard call transfers value and triggers execution in the callee's context, meaning the subcontractor updates their own storage. But a delegate call, that executes the target code using the caller's storage. It's like the subcontractor brings their tools, but they build on your lot, updating your storage slots. Knowing exactly which opcode was used is essential when you're trying to trace where a state change actually originated.
Section 4. Real-world DEX swap. Let's trace the blueprints.
Let's take all this theory and actually see it in action. Step 1. You, the EOA, sign the external transaction. Your signature hits the DEX router. Boom! You just became the general contractor pulling the permit. Step 2. The router begins executing and makes an internal call to a liquidity pool to negotiate the token movement. That's subcontractor number 1. Step 3, the liquidity pool makes another internal call to the token contract to update balances via something like, say, transfer from. Wow, okay, so that's a subcontractor hiring another subcontractor. It's a massive cascade of nested internal interactions, all sharing the same execution frame and all running on your single initial gas budget.
But wait, this begs a really important question. What happens to the entire job site if a subcontractor fails? Just imagine that step 3 fails because the token contract realizes there's an insufficient allowance. The plumber just broke the main water line. So what happens to the overarching permit?
Right, so this brings us to the atomicity rule. Usually, atomic reverts roll back the entire transaction. If that token contract reverts and the DEX router doesn't handle it, that revert bubbles all the way back to the top. The general contractor gets fired, the transaction fails, and it's literally as if the house magically unbuilds itself. None of the intermediate state changes persist. It's as if the job never started. However, clever general contractors can use try/catch blocks or low-level calls that simply return a Boolean false instead of fully reverting.
This is the equivalent of the general contractor saying, okay, look, the plumber failed, we'll patch the drywall, ignore that room, and just finish the rest of the house. The failed internal call is locally handled, the outer external transaction continues, and the final state successfully commits.
Section 5, the comparison breakdown, our master schematic.
Bringing it all together in this master breakdown, it's pretty fascinating to see them side by side. For origin, external starts with an EOA, while internal is spawned dynamically during contract execution. For nonce, external consumes a sender nonce, but internal calls do not touch nonces, meaning they can't be reordered or replaced. Visibility, external is completely visible out there in the mempool and block explorer, while internal requires advanced trace tools to observe those call frames. Gas. The sender pays for the external transaction, but internal calls just rely on whatever budget is forwarded to them. Persistence, external state changes persist if the transaction commits. Internal changes, they only persist if the outer external transaction commits, unless locally handled. Finally, reverts. External transactions have no independent revert outside themselves, they either succeed or fail. Internal calls, however, can revert locally, bubbling up or being caught. Definitely keep this in mind as a cheat sheet for your comparative capstones.
Section 6. Wrapping up with our final inspection.
So, looking back at our site inspection, 3 core principles really stand out for how Ethereum state becomes durable. Principle 1. Persistence is strictly governed by the outer transaction success. The general contractor rules the commit boundary. Principle 2. Nonces in the mempool apply only to externally signed transactions. You are never going to see a subcontractor queuing up in the mempool. And Principle 3. Tracing attribution is absolutely critical. Knowing whether an internal write was done directly, via a call in the Kali's storage, or via a delegate call in the caller's storage is exactly how you successfully debug state diffs.
So, I'll leave you with this. Can you correctly attribute the origin of the state changes in your next multi-contract trace? The next time you see a storage slot change on a block explorer, ask yourself, did this come from the permit puller or a deeply nested subcontractor? Because knowing the difference totally changes how you reason about security, ordering, and failure in Web3. That is all for today's Forge College Explainer. Be sure to head over to forge.college to put all this into practice, prepare your comparison tables, and explore more deep dive Web3 topics. Keep building, and I will see you in the next one.